Okay, let's review reactions at the alpha position of aldehydes and ketones. Some of the reactions we've learned are summarized on this page right here. So for example, if we have this ketone and we treat it with aqueous conditions, but we're not using H2O, we're using D2O under either basic or acidic conditions, so OD minus D2O or D3O plus D2O, we know that these are reaction conditions which will very quickly exchange all of the alpha protons. So if we think about this ketone, we've got an alpha carbon here, another alpha carbon there. Each one has 2 alpha protons. They'll all be exchanged by the deuterium. So the product of this particular reaction would be the per deuteration product, where all of those alpha protons have been exchanged. Likewise, we can halogenate at the alpha position using either acidic or basic conditions. Let's try basic conditions first, OH minus H2O, and we're going to use iodine as our halogen. Under these basic aqueous conditions, we're going to per halogenate much as we per deuterated. That means all the alpha protons will exchange for iodine. However, what we've discussed is that when we run the same reaction under acidic conditions, we don't see per halogenation. Instead, we only see one halogen add. In this case, the halogen is bromine. And so the product would be the monobromo ketone in this case. In order to alkylate, we've discussed the need for the strong base LDA, lithium diisopropylamide, this is lithium diisopropylamide, or LDA. This is such a strong base that we can take off one proton off of an alpha carbon, either alpha or alpha prime, basically quantitatively. In other words, with one equivalent of LDA, we can create one equivalent of the corresponding enolate and then allow that to react with our alkylating agent, which in this case is just going to be a 1-iodo-propane. And that reaction is nothing more than an SN2-like reaction. So after we remove one proton off of an alpha carbon, we'll say this one right here, to form the enolate, it will attack and will effectively alkylate at that alpha carbon. So these are 4 of the very first reactions we studied that occur at the alpha position of aldehydes and ketones, all very important. Let's talk about aldol condensations. And when we talk about aldol condensations, one of the ways we can break the discussion down is to describe aldehydes first and ketones second. And while there are lots of similarities, there's also some differences. The main difference is that aldehydes are a bit less reactive than ketones. We've discussed that before, and it really shows up here in these aldol condensation reactions. So under reaction conditions which will form an aldol product, aldehydes actually favor formation of aldol products, and those products are generally isolable. So we can isolate the aldol of an aldehyde. If we work under more forcing conditions, we can drive the aldol to an alpha-beta unsaturated aldehyde, and that's also most definitely isolated. You can see the favorable equilibrium here. We can isolate that energetically favorable alpha-beta unsaturated structure. With ketones, the aldol is not favored at equilibrium and is generally not isolable. And so we're going to have a hard time creating aldols of ketones and isolating them. For that reason, it's not a particularly important reaction from a synthetic perspective. However, We can drive the aldol to the alpha-beta unsaturated ketone, and once again, this highly conjugated system is going to be energetically favorable, and this product is isolable. So the main difference between aldehydes and ketones falls at the aldol stage. With aldehydes, the aldol products are isolable. With ketones, they're generally not. Once we drive them to the alpha-beta unsaturated aldehyde stage or alpha-beta unsaturated ketone stage, they're all isolable. Let's look at a predict the product problem here. Here I have an aldehyde, and I'm treating it with aqueous base condition. Those are conditions which should form an aldol, and we'll draw the structure of that in just a moment. Now if we maintain the same reaction conditions, OH minus H2O, but just ramp up the temperature, so a little bit more forceful conditions now, we can drive this aldol all the way to an alpha-beta unsaturated aldehyde. In this case, starting with this aldehyde, we would make the corresponding condensation product with alpha-beta unsaturation. So let's talk about how to do this in a predict the product sense first. You have to realize that the reaction is going to be between a neutral aldehyde, exactly as shown here, and the enolate. We're working under aqueous basic conditions, so we're going to pull off an alpha proton to create the enolate. So we can begin by thinking about the enolate. Think about the resonance form of the enolate where the lone pair in the negative charge is at the alpha carbon right there. That lone pair is nucleophilic, and it will attack the carbonyl group of a neutral aldehyde, forming a new bond to that carbonyl group. This carbon now is the carbon of a carbonyl group. We'll kick the pi electrons onto oxygen, eventually protonate it, and we'll have an OH group at that carbon. That carbon is still attached to the rest of the molecule, and so our condensation product would look like this. This is an alpha beta hydroxy carbonyl compound. That's an aldol. If we look at the total number of carbons, we started with 5, 6, 7 carbons. We should have 14 in our condensation product. There's 5, 6, 7, and there's another 5, 6, 7. We've got 14 carbons and a beta hydroxycarbonyl. Both of those are indications that we've drawn our aldol product correctly. Now look carefully at that alpha-beta unsaturation. When we work under more forcing conditions, we're going to dehydrate this molecule. We're going to pull a proton off of the alpha carbon. We're going to lose OH off of the beta carbon. In total, we're losing H2O, and we're going to create alpha-beta unsaturation right there. So, under these more forceful driving conditions, there's the alpha-beta unsaturation. And there is my alpha-beta unsaturated aldehyde. Let's look at the mechanism. So we started with this aldehyde, we treated it with aqueous base condition, and we produced the corresponding aldol. And then, under more forceful conditions, but otherwise the same, H2OH minus, we made this alpha-beta unsaturated aldehyde. Okay, let's study the mechanism. Here's my base, and there's my alpha protons. Those are the ones that are slightly acidic. We're going to pull off an alpha proton in order to generate the corresponding enolate. And there is the corresponding enolate. And we know that the enolate can be drawn in two different resonance forms. Since we're showing a mechanism, we should show both resonance forms. There is the second resonance form. So these are my enolates. I shouldn't say enolates plural. This is one enolate, two different resonance forms for the enolate. There are my enolate resonance forms. And now what's going to happen in an aldol condensation is that the enolate will react with the neutral aldehyde. So I need to redraw now both of those. I'm going to start with the enolate. I'm going to show it in this particular resonance form. That would be the same as this resonance form up here. We know that the carbon is going to be the nucleophilic atom in the aldol condensation, so I'm going to show the resonance form where the lone pair and the negative charge is at carbon, and I'm going to allow that to react with the neutral aldehyde. They're at equilibrium, so both are present at equilibrium. This is nothing more than any other nucleophile attacking an electrophilic carbon of an aldehyde. There's already two lone pairs on that oxygen, but when these pi electrons kick up there will be three. So I'm now going to start with this structure over here, and when the nucleophilic carbon comes in and attacks, that's going to produce an O-. I'm not going to draw that bond to hydrogen any longer. This is the carbon that attacked. There it is. It's still attached to an aldehyde group, and it's also still attached to this 5-membered ring. So if we look at that structure, you can see that this carbon, which I'm bold facing here, that was the nucleophilic carbon of the enolate, which attacked the electrophilic carbon of the neutral aldehyde to give this structure. We're in aqueous reaction conditions, so this alkoxide anion is simply going to be protonated by water. To give me the aldol, plus OH-, so I'm regenerating my hydroxide anion. So there's the mechanism for formation of the aldol. Let's continue. Remember, we wanted to not just show formation of the aldol, but then we wanted to show how it, under more forcing conditions, produces the alpha-beta unsaturated aldehyde. So far, to review, we've taken our base and removed an alpha proton to generate an enolate, which can be shown in two different resonance forms. One of those resonance forms has a lone pair and a negative charge at the alpha carbon. The alpha carbon can attack as nucleophile a neutral aldehyde. We know that must be true because both the enolate and the aldehyde are present together at equilibrium, so they're swimming around in the same solution together. When that happens, we form a condensation product. Initially, there's an alkoxide anion, which can be protonated by water in the solvent to produce the aldol product. Now we're going to take that aldol and I will redraw it exactly as I had it, or as close as I can. So there is the aldol. And we've just produced it in this aqueous basic condition, so there's still lots of OH- and H2O floating around. And you look at the carbonyl, and there, at the alpha position, there's still one hydrogen. And so it's going to be possible to create an enolate of this aldol condensation product. And so there I've done it. There is the enolate of the aldol. The aldol is nothing more than a beta-hydroxycarbonyl. It's still an aldehyde. It still has an alpha position, which has a proton on it, so it should be possible, and indeed it is, to produce this enolate. Now, as always, we can show the enolate in two different resonance forms, so we'll go ahead and do that. Oops, I'm sorry. I've lost track of my carbons there. Probably better for me just to redraw this resonance form over here. There is the alternative resonance form. Okay, well, the formation of the alpha-beta unsaturated aldehyde is just one step away. It turns out it's going to be a slow step, and the type of reaction name, or the mechanistic name we apply to this last step, is E1CB. Let's go back to this resonance form right here, and I'll show you what I mean. So I'm going to redraw that one. So there's the original resonance form I drew. There's the carbonyl, here's the alpha position, there's the beta position. Here at the beta carbon, I have this poor leaving group, an OH group, and because it's a poor leaving group, the step I'm about to show is somewhat slow. And that's why when we're working under forceful, that's why forceful conditions are required under these aqueous basic conditions. We've got to form this alpha-beta unsaturation with expulsion of this leaving group, a poor leaving group. Not necessarily an easy thing to do energetically, and that's why the reaction condition requires a little extra heat. When we do it, the good news is we form a compound which is stable. This alpha-beta unsaturation allows for a conjugated pi system, and that's why this last step, the E1CB, favors formation of the corresponding product. Now, why do we call this an E1CB? Call it an E1CB because the reactive species, this enolate, is a conjugate base. How did we make it in the first place? We made it by deprotonating an alpha proton. So this aldol product is the acid, specifically this proton on this carbon-hydrogen bond is the acidic proton. If that's the acid, then this species here is the conjugate base. Once you pull the proton off, you generate the conjugate base. The conjugate base eliminates the poor leaving group OH- in an E1 unimolecular elimination reaction. And as I mentioned, it's a little bit slow, so we jack up the temperature just a little bit, and that helps us force formation of this product. Because the product is stable, once it's formed, it's less likely to revert, and generally speaking, we can drive our aldol all the way to this alpha-beta unsaturated carbonyl in high yield. Okay, let's review now. Acid versus base catalyzed aldol condensations. So first we'll start with an aldehyde. We've already mentioned that aldehydes are a little bit more reactive than ketones, so we're going to break the discussion down into aldehydes and ketones as well. But we begin with an aldehyde. Consider the basic condition versus the acidic condition. In both cases, we can generate an aldol that's favored at equilibrium and is isolable. So aldols from aldehydes, regardless of whether they're run under basic, the reaction is run under basic or acidic conditions, those aldol products are going to be isolable. If we want to force them all the way to the alpha-beta unsaturated aldehyde, under basic conditions, we're going to have to increase the reaction temperature. However, that's not true under acidic conditions. Under acidic conditions, the aldol product will just naturally continue to react all the way to the alpha-beta unsaturated aldehyde. For that reason, if you look at these equilibria carefully under these acidic reaction conditions, we're not going to be able to stop at the aldol stage, not because it's not isolable, it would normally be isolable from an aldehyde, but simply because the reaction continues under the exact same reaction conditions to the more energetically favored alpha-beta unsaturated aldehyde. So under acid conditions, we're just going to fall naturally all the way down here. Under basic conditions, we can, if we want, stop at the aldol stage, or by applying slightly more forcing conditions, push it to the alpha-beta unsaturated aldehyde. Ketones are similar, with the caveat, as we've already discussed, that the aldol is generally not isolable from a ketone. The equilibrium doesn't favor aldol, whether we run it under basic or acidic conditions, and you generally can't isolate it. However, all other parts of the reaction are the same as discussed with aldehydes. So if we're working under basic conditions, we can be a little bit more forceful, apply some heat, and drive it favorably all the way to the alpha-beta unsaturated ketone. Under acidic conditions, the exact same reaction conditions just naturally lend themselves to formation of the alpha-beta unsaturated ketone. We don't have to apply extra heat. So ketones, under basic conditions, will not form an isolable aldol. However, it will be present at equilibrium, and if we want to, we can drive it to the energetically favored alpha-beta unsaturated ketone with some heat. Under acidic conditions, while the aldol is not favored at equilibrium and is generally not isolable, it will nonetheless continue all the way to the alpha-beta unsaturated ketone, which is favored at equilibrium and which is isolable. So that's a different way to break it down, acid versus base catalyzed aldol condensations. Finally, let's look at Knoevenagel condensations. Knoevenagel condensations are going to occur when we have a compound like these shown on the page, which have an unusually acidic CH proton. So this would be true when we have, for example, beta dicarbonyl compounds. This one is a beta diketone, this is a beta diester. Beta dicarbonyl compounds will have, in the case of the beta diketones, 3 different types of alpha protons. Let's look at these alpha carbons, all of which have protons on them. We've got alpha in the middle, alpha prime on the left, and alpha double prime on the right. This alpha carbon in the middle is the one that's special, because this alpha carbon is sandwiched between 2 carbonyls. And that makes these protons right here unusually acidic. Alpha prime and alpha double prime, on the other hand, they're more like traditional alpha carbons with traditional alpha protons attached. They're only adjacent to 1 carbonyl. These right here, these alpha protons in the middle, those are the ones that are unusually stable. Unusually acidic. The enolate which will form is going to be an unusually stable enolate, which is why these protons are unusually acidic. That would be true for a beta diester and other beta dicarbonyl compounds as well. But it's also true for a few other types of compounds, like for example, this cyclopentadiene. These protons are unusually acidic because when we remove one, we produce a cyclopentadienyl anion, which is aromatic. So there's special electronic reasons for the stabilization of this anion generated upon removal of one of these protons here. Other compounds are unusually or have unusually acidic protons because of functional groups that are attached. Like for example, this nitromethane molecule. Here I've drawn one of the carbon-hydrogen bonds out, but in truth all 3 of these carbon-hydrogen bonds at this methyl carbon would be unusually acidic. Doesn't matter which one you pick. And that's because they're adjacent to this nitro group, and the nitro group has this positively charged nitrogen atom. This is a bit like being adjacent to a positively charged carbocation. We know that if we had a carbocation, the protons at the alpha carbon would be unusually acidic, and here the protons at the carbon alpha to the nitro group are also unusually acidic. And then finally, down here, we have a compound, simple compound, this dicyanoMethane compound. Two of these cyano or nitrile functional groups are attached to the same carbon. Now, we've talked in the past that although the carbon-nitrogen bond is a triple bond, it behaves a bit like some of our carbonyl-containing functional groups, like carboxylic acid derivatives. And we've looked at some of those chemistries. And so that's the way you should think about it here. When you see a nitrile group, you should think of it essentially as a disguised carbonyl. So this kind of a molecule is nothing more than a carbon sandwiched between two disguised carbonyls, very similar to a beta-diketone, for example. So this carbon here, this we could call it an alpha carbon, is going to have unusually acidic protons associated with it. Okay, let's look at a typical Knoevenagel-type condensation. We're going to take one of these molecules which have unusually acidic protons, like this beta-diketone. We're going to allow it to react with an aldehyde or a ketone, in this case an aldehyde, it would be benzaldehyde. And our base is a relatively weak one, triethylamine. We can get away with a relatively weak base in this case because these protons are acidic enough to be deprotonated by an amine. The reaction product is going to be the corresponding alpha-beta unsaturated carbonyl system. So there's not going to be an aldol, an isolable aldol product here. These reactions will go all the way to the alpha-beta unsaturated carbonyl. Okay, here we go. Let's look at the mechanism. Our triethylamine is going to come in, pull off one of those unusually acidic protons. And we're going to have the corresponding enolate. Now we can draw multiple resonance forms here. There's one of the resonance forms, in addition to the original resonance form. And now I can show the third resonance form, which places the extra pair of electrons and negative charge at the other oxygen atom. So one of the reasons that these alpha protons sandwiched between two carbonyls are unusually acidic, more acidic than a traditional alpha proton like that one or that one, is that we generate a more stabilized enolate species. Generally speaking, the more resonance forms you can draw, in this case 3 resonance forms, the more highly delocalized the system is and the more stabilized it is. Okay, so there is our enolate. I'm going to go ahead and redraw the enolate. And once again, I'm going to choose the resonance form in which the lone pair in the negative charge is at carbon. And we're going to allow it to react with our benzaldehyde molecule. And when that happens, see this new bond I've just drawn there, that's the key bond, that's the new carbon-carbon bond. So that lone pair right there is now tied up in this new carbon-carbon bond. It has attacked the carbonyl, so now I have an O-. I'm not going to draw that carbon-hydrogen bond, but I will of course draw the benzene ring or the phenyl group. This looks like a traditional aldol condensation. We've formed an alkoxide here in this first step. I should say in this second step. The first step, we deprotonated using triethylamine, and in the process we would have generated a triethylammonium cation. We can use that triethylammonium cation right now. To protonate this alkoxide. And now we've got an aldol. Because counting from either of these carbonyls, this would be alpha, this would be beta, this is a beta hydroxycarbonyl. This is our aldol, but it's not going to stop here. The reaction will not stop here because at this alpha carbon, I still have an unusually acidic proton, and I still have triethylamine. I generated another equivalent of triethylamine here in this last reaction, but there's also going to be plenty of it around, floating around in solution. This generates a new enolate species, which is shown here. And now for an E1CB, just like we saw a few moments ago, we've got this lone pair negative charge sitting at this alpha carbon. We can take the lone pair and form a new alpha beta unsaturation, a new pi bond between the alpha beta carbons with simultaneous expulsion of the OH minus. Now in this case, it's a reaction that will not generally require extra heat, and that's because if we look carefully at the product that forms, which is right here, this is a highly conjugated pi system. The molecule is stabilized by this conjugation. That means energetically it sits at lower energy, and likewise the transition state leading to it would sit at lower energy. It's an easier E1CB reaction than those we would see with a standard aldehyde or ketone molecule. So we don't generally require extra heat in a Knoevenagel condensation because we're getting such a stabilized, highly conjugated product. The reaction proceeds under milder conditions. Okay, so we've looked at Aldol condensations and Knoevenagel condensations, which are very closely related. Let's wrap this up by talking about a synthesis problem. Now that we know about Aldol condensations and Knoevenagel condensations and the like, it means we can add an extra wrinkle to some of the synthetic problems, the likes of which we've been tackling in recent weeks. So for example, we should be able to take this 4-carbon alkene and convert it into this aldehyde. And at first glance, this looks like a pretty complicated structure, but looking at the carbonyl carbon, we realize that that's an alpha carbon, that's a beta carbon. This is nothing more than an alpha-beta unsaturated aldehyde. The very type of product we now know how to make through Aldol condensations and similar reactions. In fact, if we break it down even further, we realize that this had to be, in other words, the immediate precursor of this particular alpha-beta unsaturated aldehyde had to be a 4-carbon aldehyde. There are the 4 carbons of the aldehyde, and there's the other 4 carbons of its partner that it condensed with. In other words, this alpha-beta unsaturated product came from this exact aldehyde right here. Plus what? Plus nothing. Think of it this way. If that is the enolate that we would produce from this particular aldehyde, let's allow it to react with another aldehyde, a neutral aldehyde. And I think you can see that the first step would look like this. We would create a new bond between these 2 carbons. Now look carefully up at this structure. There's the aldehyde at the alpha carbon. That's where we have our nucleophilicity. We're going to produce a new bond to this carbon, which becomes the beta carbon, initially to form an aldol, but after some further chemistry, we get alpha-beta unsaturation there. So really, all we need to do is figure out how to convert this into that aldehyde, and from there, we can go to the alpha-beta unsaturated condensation product. We could do it in two ways. We could either use OH minus H2O and some heat, or H3O plus H2O. So the problem then reduces to one of solving this synthesis. Can we convert this alkene into this aldehyde? Now we're going to have to use some chemistry that we learned a couple of weeks ago, but this is actually very doable. Not all that difficult, really. We need to put an aldehyde at that carbon, so we're going to begin by putting an alcohol at that carbon. How do we do that? This is an anti-Markovnikov hydration. We can do that. We've done that many times. And now we need to oxidize this to the corresponding aldehyde. How do we do that? This is a reaction where we want to be careful that we don't over-oxidize all the way to the carboxylic acid. We don't want to use wet oxidants. We want to use dry oxidants like PCC. And that would complete our synthesis. All that's left is the condensation step. Done. Okay, I hope you found this review helpful. I'll see you soon.